Okay, so this tutorial is going to be set up for creating an animation and a deformation rig pipeline. So basically what I'm going to do here is I'm going to take what I have, which is an animation skeleton, and let's just unhide both of these. I'll tell you what this thorax thing is doing in a second. Alright, I have two groups here. I have an animation group and a deformation group. Right? And that animation and deformation group are part of my dual pipeline system. I have an animation skeleton, which I'm going to get all my mocap and other data from. Any type of hand animation will go into this animation pipeline. The deformation pipeline is a completely different skeleton, or at least it's an expanded skeleton with all kinds of extra nodes. Specifically in this tutorial, we'll be going over these twist nodes and how to drive them with an animation skeleton. And this is pretty advanced rigging stuff. This is where the professional riggers really show their expertise in creatively solving certain problems with various forms of data coming in from mocap and having to set up a deformation skeleton that works for a particular model. So this dual pipeline allows us to use one skeleton for all animation materials or purposes. We can take mocap data and put it on here, and we can do hand animated data and put it on here, and then we have a deformation skeleton which basically rides on the top of that animation skeleton. And that deformation skeleton can be unique for each independent character for whatever needs they have. I can add tentacles, so this was Dr. Octopus here. I can add some tentacles along the sides and put that on top of my deformation skeleton. I can also add a whole lot of extra joints like muscle joints. I can add custom deformation lattices or muscles, these Maya muscles here and bones. You can do anything you want to the animation skeleton, and yet to the deformation skeleton. You do anything you want to that to get your character to deform properly, but at the same time, your animation skeleton remains the same. So you can take the same mocap data and put it on any character you want. Alright, so what we're going to do today is work on, first of all, just understanding how to pipe this animation skeleton into the deformation skeleton. And why we have two skeletons here for this particular purpose is this problem, the twist problem. Very common problem. We're talking about bipeds. The humerus rolls in its socket, and then the skin underneath the socket, where this pectoral muscle here and this deltoid turn into the bicep where it inserts itself, this skin here peels off and rolls. Now the problem is we have a joint here in any conventional skinning method, and let's just hide our deformation skeleton, because here's our problem with the animation skeleton. And just ignore these locators here. I'm going to tell you what they're doing in a moment. Alright, so here's our animation skeleton. I've set up a pretty good bind. We can move them up here. It's not perfect, but it's pretty good, solid bind. When I rotate my humerus back and forth across this plane, or if I want to rotate it down with his arm to the side. The place where this particular binding fails miserably, and let's just zero these out, is when I try to rotate it on the spindle axis. And remember, our humerus is a ball and socket joint, and it does rotate in all three planes, which makes it really difficult to rig. And you can see it completely breaks it here. There's just no way to roll this joint from this particular point, this pivot point, without completely breaking the shoulders. They're called breaking it because it looks like it's imploding on itself. So basically what we want to do is we want our arm, this arm is really beautifully modeled to get this nice twist going. We want it to twist from this span all the way down to this span. And just because of the nature of the skinning and how the skinning cluster is calculated, if we try to twist it from here or here, we get what's called a candy wrapper effect. So where are we going to twist it? Well, up here we have this problem where, yes, we're twisting it and breaking the shoulder, and if we try to twist it, the wrist has the same problem. It basically breaks the wrist. So we need these extra twisting nodes. Now the problem is animating those twisting nodes is really difficult, and it's very difficult to set up IK solutions where all of those are locked. So by lifting that deformation skeleton and completely away from our animation tool set, be it IK or motion capture or a combination of both, it lifts it up and allows us to do things where we can take the X rotation of this humerus from the animation skeleton And let's bring up our deformation skeleton here. And we can put it onto 1, 2, 3, 4 breakaway split twist nodes. We usually call these twist or roll joints. All right, and so now you see the bicep can swivel the way it does in real life, and it's a little bit, I could work on the skin weights a little bit. Remember, we're only working on the amount of natural motion, and honestly, your bicep can never do that. So we always look at this, your bicep can't do that. Your bicep can only go from its position about here to, it can definitely roll almost all the way downward, and it can roll about up to there. Anywhere past there is really going to break your shoulder. So you got to look at the natural range of motion with which we're trying to edit. Now, I've worked on all the skin weights here to get all of these twist nodes in place. Now what we really want to do is drive them with the animation skeleton and allow the twists to happen naturally with animation data we then bring in. So in order to do that, we're going to set up a little rig here. Now the first thing is to create a pass-through rig. And this deformation skeleton can become whatever we want. We can keep adding bones and adding skin weights and adding blend shapes and adding all kinds of stuff. The really advanced rigging stuff. But what we really want first is to create the pass-through, or we create the constraints between our animation skeleton here. And let's just unhide that. And the deformation skeleton. And I'm going to hide our animation. Now notice I have a Spider-Man Geo that's been bound to the animation skeleton just to show the difference between the deformation, the animation skeleton, and then the deformation skeleton when it comes to deforming our model. So I've got one bound to the simpler skeleton and one bound to the higher resolution skeleton, or the deformation skeleton. And there's a lot of complex stuff going to be happening in this tutorial, so you might want to play it again and kind of go through these pieces one by one and see how this works, because it's a very important lesson in how to really create some professional data streams and create a rigging setup that allows you to freely change those deformation skeletons to match the needs of the character while maintaining a single animation skeleton. Okay, so what we're going to do now is I'm going to create constraints between that animation skeleton and deformation skeleton. This means the deformation skeleton is going to ride on top of the animation skeleton. So first of all, I'm going to select my ani root and my deformation root. I'm going to constrain and I'm going to click on parent. Now for the purpose of this tutorial, we're always going to use this maintain offset. There are places where this could be a problem, but generally speaking, this allows us to keep the current position of the skeletons. The current transforms of our constrained skeleton, it's not going to move it. We should have this set up so that this doesn't need to happen, that we don't need an offset. But just in case, especially for some of the orient constraints around the wrists, which have slightly different joint orients between animation and deformation skeleton, this is going to be kind of helpful. So I'm going to go ahead and click on add. Now, this is the only parent constraint I'm going to make between these two, because it's the only part of our skeleton here that needs to translate. Everything else is a rotation. So now we're going to go up that spine here. And let's just make this a little less complex and looking. So I'm going to select my animation spine, and then my deformation spine 1. And we're going to go to constrain orient. Once again, let's make sure maintain offset is on. Okay, now I will do that with the spine. Now make sure you select these in the proper order. The spine, the constrainer, or the object that is constraining, or we also call it the target, and the constrained object. Now we'll move on to spine 3. And now we will do the clavicle. So animation left clavicle to the deformation left clavicle. Constrain, orient. Okay, now here's where the tricky part happens. And actually, before we do the tricky part, let's just do the elbow to the elbow. So I'm selecting the animation elbow, the deformation elbow, and let's orient, constrain it, and then let's do the wrist. I like to get all these out of the way first. And I'm doing this kind of fast, and you can see that there's a whole bunch of crap here in my outliner, and it gets really confusing. So be very careful and slow with this. make sure that you set up constraints properly. It's very easy to select the wrong two joints and create a constraint, and you have to dig through all this stuff to find it. Okay, so now the tricky part. Okay, what we really want to happen here is that we want our deformation humerus to move with our animation humerus, but we don't want it to move on this rotate X plane. Right? We don't want that to happen. And right now, because we haven't constrained that humerus just yet, you're seeing the elbow move, but the humerus is not. Okay, so we don't want that. We don't want the deformation humerus to roll on the X axis. We want the deformation twist nodes to roll, to separate that value by 4 and roll independently. And then they will radiate out from this point here and rotate that bicep in a much more natural manner. Alright, so the tricky part is the aim constraint. Right, the aim constraint, and something happened over here. I'm not quite sure what. Let's see here. It's my thorax root. And there we go. I'm not quite sure how that got offset. So what I'm going to do here is just delete that for a moment and make sure that it's not going to hurt anything. All right. Sometimes when you're recreating these, you have to go back and fix what you set up originally. And I'm going to go over these in just a moment. Okay. So now what my plan is to take that animation elbow, right? And I'm going to take my deformation humerus and aim it to the animation elbow. Now, I'm not going to go into a lot of the mechanics of why this works, but what happens is when you rotate the animation humerus, what will happen, and ignore that for a minute, I'm going to show you what's going on here. All right, rotating the animation humerus will move, remember, it will translate the animation elbow in an arc around it, just like our kinematics works. Okay, so if we aim the deformation humerus to the animation elbow, it will act as if it's parented, as if it's following it, or as if it's moving with the animation skeleton, with one very, very important exception. And that exception is that the rotate Y will not change, and the reason for that is that when one object is aimed to another, and it's always in its direct line of sight, there's no reason it should move or rotate around its own axis. Now, because of the nature of the setup, and because this guy is in the A stance, we've got to do a little creative aim constraint parameterization, or basically we have to set this up so that our aim constraint works properly. And that's so that it doesn't artificially roll. And this is a part that gets a little confusing, and you won't have to worry about it too much, except that I'll just show you how I've set this up. Okay, we're creating an aim constraint. But now that aim constraint has to be told where the rotation up is. If it doesn't know this vector, and I'm kind of drawing a line for this vector here, if it doesn't really know what this vector is, it won't take the X rotation out of the humerus. So what I've done is set up a system upon which this is receiving its coordinates. It is parented to this thorax. Oh wait, that is a thorax root. Now what has happened to mine? Oh, okay. Sorry, that's not a thorax root. Let me rename that. And that is the left humerus up object parent. Now why does that matter? Don't worry about it too much. It's not that important. The important thing is it is point constrained to that humerus, so it's always moving with the humerus. And because it's always moving with the humerus, and it's getting its position relative to the thorax, this object will always represent the up vector for the aim constraint I'm about to create. Now, it's a lot like joint rotation. Basically what I'm telling it to do is to make sure it maintains this line of contact with this point here, which is directly in line with this joint's orient. And that's going to make sure that it never rotates on the x-axis, or it rotates very little on the x-axis. And it's going to set up my aim constraint to operate properly. So now what I'm going to do here, the easier part, is that I'm going to select my animation left elbow. Alright, and then I'm going to select my deformation left humerus. And we're going to make an aim constraint between here and here. And what we're going to do is, we're going to use this as the world up object. Just means that the up vector, instead of being here, which is the world up, is going to be here, which is the object up, and that's going to make my aim constraint work the way I want it to. So first of all, in order to do this, and Maya does not make this easy to do, I'm going to have to copy the name of this, just so I can paste it in the dialog box. So let me go back and select my animation elbow and my deformation humerus. Okay, now we will go to constrain, aim. Okay, now once again I'm just going to go back over this. What I'm doing is I'm creating a constraint, an aim constraint, which is going to aim the deformation humerus to the animation elbow. In effect, making this shoulder move with the animation skeleton, except it's not going to rotate on that x-axis. And I'm doing that by creating an aim constraint and using this object here, which I have set up previously, to be in line with this object's orients. Now you can see here I've got maintain offset on. We're always going to keep that on in this particular instance. All right, and that means all constraints set up between the animation and skeleton. If we're staying within Maya, we'll leave this maintain offset on. Okay, so my aim vector is 1. This is just like a joint orient, primary axis, right? The x-axis is flowing down here. Our up vector being y, here's our up vector, because the y of the joint is, this is the up. And that's why we're using this object up, which is this object here, and we can give it a custom up so that it doesn't accidentally roll on that x-axis. And this is very important, otherwise the intent of this whole setup with the aiming of the humerus to the elbow basically isn't going to work. Okay, so I'm going to make sure I'm on all axes, and I'm going to click on add. Alright, so now let's test this out here. What's going to happen is, and I'm going to grab my animation skeleton, and I'm rotating. And yes, it's rotating, so my deformation skeleton is rotating exactly the same as the animation skeleton. And you might ask yourself, well, big deal, so what? You could have done that with an orient constraint, or from the humerus to the humerus, or with a parent constraint. Why does it matter that you have this as an aim constraint and you have it set up so that it never rolls on this axis, right? So now watch, until I put that rotation on these 4 twist nodes, the elbow is going to rotate without the rest of the arm rotating. So what we're going to do is take that rotation and we're going to split it down the middle here. Alright, how do we do that? It's pretty simple. What we're going to do is we're going to select our little twist nodes here, and we want to derive the x, or the spindle axis rotation of our animation humerus, and split it into 4 values and put it on our twist nodes. So we're going to do that with an expression. There are more than 2 ways. There's at least 3 ways to get that value and divide it by 4 and put it on these joints. And this is not even the best way, but it's the simplest way to show you. And we haven't used math nodes yet, so I'm going to stick with what we know, which is the expression. So right now I'm going to go to my attribute editor. I have my def left hum twist 1 node selected. And I know this gets confusing when you have 75 bones and you have these 4 twist nodes. If you think it's confusing just setting this up, try skin weighting all these joints. Really tough to do. But when you're done with all this stuff, you get a really nice result. So it's worth the extra effort. Okay, now I'm going to create an expression. And that expression is going to take this value, or this object's rotate x. We're only dealing with the rotate x because we've made that the spindle axle, or axis, excuse me. So I'm going to grab this and middle mouse and drag it down here. That just puts the text of the attribute in the expression editor. And this is a lot like scripting. Here's our variable or attribute we're putting this on, and I'm going to call it Annie underscore left underscore humerus dot rotate x, and let's put that in parentheses, and then over 4. And that's it. We're splitting that value into 4. Now we'll create it. You can see the expression is being created because it's yellow. Now what I'm going to do here is select the one beneath it, select that channel, and I think I actually forgot to copy it from the previous one, so let's just do that again. I'll copy it this time. equals parentheses and underscore left underscore humerus. Now see, I'm a terrible typist, which is why I use copy and paste all the time. And over 4. And this time, I'm going to copy that. Let's create that. And now let's select the next joint. And now we can just paste it and change 2 to 3, because this is the def left hume twist 3. So we'll just change that number to 3. And let's select that one. Make sure we're in the right channel here. And we'll just change that to 4. Now this does get confusing, and I'm doing it kind of fast, but man, you really want to take your time when you're doing these things, the same thing for multiple objects, because you want to make sure you have the right node, the right name. It's a lot like coding. You want to make sure everything is right, because you don't want to come in problems when you typed in the wrong name, or you forgot to change it from 3 to 1 or whatever. Okay, so now, just quickly, let's see how that works. And there you go. And it nicely allows you to match the Z and the X, sorry, the Z and the Y movement of the animation humerus, but roll that bicep without rolling the humerus here. And just to show you how awesome this works, I'm going to bring up the animation skeleton, animation humerus, or the animation model that I bound in the animation skeleton. And then and I'm going to grab that. And you see how badly it's deforming this up here? Now let's just see what the deformation skeleton is doing, or the deformation version. Now it may need some tweaking in the weights here, and this is pretty far, but notice how the delts are keeping their shape here. And this is the animation. Okay, so now notice how nice, it's a little hard to see here, but notice how nicely this is keeping its shape. If I hide that, notice how badly this is keeping and maintaining its shape. Alright, what a tremendous difference you get when adding those twist nodes, because it completely removes that horrible, horrible broken shoulder thing going on. And you're going to get animation, especially if you're a mocap, that it's going to twist the arm like that. That's not an unnatural arm position. That is a very natural arm position. So I'd much rather see that than that. Right, much better. And yes, it is a pain to set up, and yes, it does take some time. But, and then maybe just with a little tweaking on the skin weights here, which I might work on later, the results are tremendous. It's a tremendous difference between one and the other. Alright, so now the only one we have left here, and let's just zero this out here, is to do the same thing to our twist nodes. Now the nice thing is we don't have to do that aim constraint. The only place we need to do that aim constraint is the humerus to the elbow. And any other joint anywhere else where you may need to take out Y rotation, or not Y, excuse me, X rotation, or whatever the spindle axis is. When you want to remove that and use a series of twist nodes, for instance, the femur, which is the top of the hip, that's an area where people use these rolling joints too, and then as well they should, because the same thing is happening here. Only a lot of characters don't really need that much detail in the leg, so I have not put it in here. But if we did need that much detail, that would be once again a reason to have this deformation skeleton, which rides on top of the animation skeleton. And if I had a character that needed that, I could certainly make his own deformation skeleton based on the animation skeleton, and I could use one set of animations for multiple characters. And this is how things in games are done all the time. We really don't have the resources to have separate animations for every character. You know, some have global animations like walk cycles and stuff like that. Okay, so what I'm going to do here, and this should be pretty easy. Same thing as I did with the twist nodes up there. Let's create a new expression. make sure we're on the rotate X and drag that down here. And we're going to call in underscore left underscore wrist. This is why everything gets named, because you have to be able to type these names out. Rotate X over 4. And I can go ahead and copy that. And make sure I change all these names. Once again, if you don't update that name, it will give you an error message. Or even worse, screw up this node where you have to go back in and fix it. And more here. Rotate X. Alright, and now the exact same setup has been created with the wrist, where instead of getting that horrible, ugly, broken wrist, we now get a rolling forearm. And it's never going to be 100% perfect, but once again, let's just bring out that. And I'm going to hide that for a minute. Now look at that. Let's grab our animation wrist. Alright, would you rather see this or this? Granted, like I said, not perfect, however, major improvement on the wrist. The wrist no longer looks terrible and broken, it actually looks pretty reasonable. Okay, so let's zero that out. Alright, so that's a quick crash course in creating this dual stream or dual pipeline system where you've got one skeleton riding on top of another one. Now, like I said, we can do anything we want to this deformation skeleton. We can have all the setup, all the complex layers of animation setup on this deformation skeleton, and we never, ever have to change our animation pipeline. One skeleton rides on top of the other, so the animators can work with that skeleton. They can animate something simple. They can create their own edit rigs and animation rigs and all those kinds of things, and then bake all those on an animation skeleton, and we will always have the same animation skeleton, whereas we can continue to change, add, update, or make different versions of our deformation skeleton.